Hello, everyone. Good afternoon. My name is Yanjun, and this is Xie Xingguo. We are from ZTE Corporation. Today, we are going to introduce a kind of recovery bandwidth control method that is based on dmClock. Okay, there are three parts in this topic. The background, design and implementation, test and result. Let's talk about the background first. What's the problem we are going to solve? Okay, we all know that data recovery has a great impact on client performance in Ceph. However, on one hand, users don't want client performance to drop too much when the class is undergoing data recovery. Since high performance is always welcome. From this point of view, they may want to delay data recovery and slow it down. On the other hand, data recovery means the cluster falls into a local film. That will reduce the reliability of data. So we have to get it back to OK as soon as possible to reduce or to lower the risk of data loss. Then it's necessary to find a way to balance, It's necessary to find a way to balance the client OP with recovery OP and try to minimize performance impact on the client, and meanwhile, complete data recovery as soon as possible. Actually, there are two main goals for client performance reduction. First, reading a degraded object on primer PG will cause the primer to pull the correct object from replica to recover it. Similarly, writing a degraded object to the replica PG also requires pushing the correct one to the replica first. Read and write OP will be blocked until the degraded object is recovered, which results in great performance reduction. This is the first cause. And fortunately, it will be solved by a single recovery and the incremental recovery in the near future. The second cause is that recovery is a large size OP. And if there are lots of recovery OP, it will take most of the disk bandwidth. And if we increase if we increase the concurrence of PG recovery to speed up data recovery, things will get worse. So we try to introduce a recovery bandwidth control method to handle it. And this topic focuses on it. Okay. The main idea is to control recovery bandwidth of the OSD, since the recovery OP is more aggressive. We limited the recovery bandwidth to 3 different levels: lower, middle, and high. As the disk bandwidth is almost fixed, the rest of the bandwidth is available for client OPs. The main idea consists of 3 parts. First, we try to find a bandwidth control method. Here we use the dmClock. Based on that, implement per-osd recovered bandwidth control. Then figure out a class-wide bandwidth control strategy. Okay. First of all, let's talk about the dmClock. dmClock is a distributed quality of service algorithm authored by Mr. Gulati, Mercer, and Wellman. It has been implemented in C++ by Eric. It has been merged into Ceph in this PR. And 2 experimental sharded OP queue are added here, which is mClock OP class and mClock client. Also, it has been used as a HW scheduler in another PR here. So originally, dmClock support I/O reservation, weight, and limit, but not the bandwidth. So how to implement bandwidth on dmClock? As similar to the calculation of limited tag, we get the bandwidth tag calculation formula. Here is the calculation formula. The letter B is the target bandwidth of a client. The word size means the size of the current request. And the phi is the incremental size completed by other service. Let's start with this simple scenario as below. Here is just one server. So there is no incremental size phi at all. In this example, the client's target bandwidth is 40 kilobytes per second. Yeah. It sends I/O request to the service in such a sequence. Request 1, 2, and to 7. The request 1 is processed at the time T1 here. And the subsequent request will be processed later after the last one according to the own size. Request 2 is 4 kilobytes, so it will be processed at 0.1 seconds after request 1. Request 3 is 8 kilobytes, so it will be processed at 0.2 seconds after request 2. So does the request 4, request 5, and others. So in this way, we finally, Okay. So we finally achieve what we want, the bandwidth recover. Okay, let's say the distributed scenario. There are multi-service now, so the incremental size should be taken into account. In this scenario, requests are randomly sent to different services. Request 1 and request 4 are sent to service 1. Request 2, 5, and 6 are sent to service 2. Along with the request, the incremental size is also sent by client. The incremental size here is the total size complete by other service after the last request. Let's take a look at request 4 here. Its last request is request 1. And so the incremental size is request 2 and request 3. 4 plus 8, that's 12 kilobytes. Plus the ON size of request 4 kilobytes. That's 16 kilobytes of all. So the request 4 will be processed in 0.4 seconds later after request 1. And the incremental size of request 5, that's also 12 kilobytes. So this is the distribute scenario. Okay. Based on the dmClock bandwidth, we now try to implement per-osd recovery bandwidth control. Firstly, let's see the original mClock OP class and the mClock client queue. The OPs has been divided into 5 types. Client OP, sub-OP, recover, and scrap a snap tree. Each type has its own QoS parameter. These 2 queues are the sharded OP work queue type. They have multi-sharded queue. Each of them works as a standalone service. So the OP will be processed independently in each service queue. That's why the 2 queues still named after mClock, but dmClock. Okay. The main difference between these 2 queues is the client OP. Okay. For this mClock OP class queue, all the OP from different clients are treated as from one client. And for the mClock client queue, each client has its own QoS parameter. Then, based on the 2 queues mentioned above, we introduce a new dmClock queue here, which is also sharded OP work queue type. For the OSD that receive recovered data from others, we added a new pull push OP type and a visual class for them. All the pull push OP from other OSD are treated as from the visual client. We can set the target recovery bandwidth for the visual client. So there are this multi-sharded OP service work together to achieve the OSD's target recovery bandwidth. Now we can set different target recovery bandwidth for an OSD as need. Here is ranked into 3 levels: lower, medium, and high. A load monitor and an adjuster are introduced to OSD. They monitor whether they are a client office or a recovery office or not. Then we get 4 load states. The active that have both client OP and recovery OP. A client that have client OP only, and recovery that have recovery OP only, and ideal they have either of them. So according to the load status, they just select different recovery bandwidth levels. That's the lower, middle, and or higher level. Finally, we present 3 different cluster working modes for users to choose as they need. That's client prioritized, recovery prioritized, and self-adaptive mode. As the name shows, client prioritized mode tries best not to reduce client performance. So the OSD are limited to lower level recovery bandwidth. And in the recovery of priority mode, OSD are set to higher level recovery bandwidth to complete data recovery as soon as possible. As for the self-adaptive mode, OSD are set to a proper recovery bandwidth according to the load status. And in this mode, all the 3 levels maybe exist in different OSD of the cluster. Okay. Let's talk some more about the self-adaptive mode. When the cluster selects this mode, if the load status is active, OSD may be all limited to the same medium level. The OSD with more objects to recover will take longer to complete recovery than those with less objects. So we can make further adjustment. From the PG status reported by OSD, MGR knows how many degraded objects need to recover per OSD, and then figure out the adjustment factor according to that. For example, there are 300 degraded objects in OSD 0 and 200 in OSD 2. With an average of 250, the factor of OSD 0 can be 1.2, and the OSD 2 can be 0.8. After this adjustment, the OSD tend to complete data recovery at the same time. This will shorten the whole recovery time of the class. And finally, we test these 3 working modes in one of our cluster. In this test, they are about 1.2 terabytes data to recover. During the recovery, we keep the client's performance stay around 10,000 OP per second. As expected, the I/O latency is minimal in the client prioritized mode, but it takes over 30 minutes to complete data recovery, while it's just about 6 minutes in the recovery prioritized mode. For the self-adaptive mode, the I/O latency and the recovery time are both in the middle of the 3 bonds, so it could complete data recovery relatively quick and with little performance impact on client. That's what we expected. Okay, that's all. Thank you.